And if you know anything about Waterloo, it's a very good place to do quantum computing and physics and computer science in general, but it's also a very cold place and relatively a small town. So after spending 2 years there, I thought that it would be a really good idea to spend part of my PhD in Sydney, and I enrolled into a double PhD program between University of Waterloo and Macquarie University. So when people think about Sydney, they think about the lifestyle, the great weather, the opera house, but you might not know that Sydney is actually a really great place in computer science. We have many people who work on all the aspects of quantum computing. We have many different labs, optical, nanotechnologies, silicon qubits, everything you can possibly imagine. Very strong computer science aspect of quantum computing, and also a lot of theory. So all of these people are only one of the very few that are members of the quantum computing community in Sydney. And together, there are 4 universities in Sydney that are heavily working to bring quantum computing to life. Amongst them, there are more than 70 faculty members, so senior academics, who all work in quantum computing or related technologies, and many more postdocs and students. And last year, we tried to really put Sydney on the map of quantum computing by kickstarting Sydney Quantum Academy. So all 4 universities are now trying to work together to help students to gain the education to be successful in quantum computing, and also to build a bridge between the academic research and industry. So if any of you are interested in pursuing an academic career in quantum computing, a round of PhD scholarship is open right now, and we will have another call later in the year and possibly and also in the future years. And we are also always looking for talented postdocs and industry partners. So there is a website where you can find all the information, or again, you are very welcome to talk to me about Sydney Quantum Academy later. Right now, I am a postdoc at University of Technology Sydney, and I work with these 4 lovely people, amongst them Professor Bremner, and we are in the computer science department. So when people think about quantum computing, they usually think about physicists making quantum computers and bringing them to life. But there is a very computer science aspect to quantum computing that can tell us about what is the power of quantum computers and how can we fairly compare them to classical computers, which is what we are working on in our group. Okay, so when we talk about the applications of quantum computers, we are in fact talking about 2 fairly distinct questions. One question is, what are the problems that we can solve more efficiently if we have a quantum computing chip with some large number of qubits? And here we will assume that the qubits are quite good, but maybe not fault tolerant. And this is very different than asking what are the problems where quantum computers would eventually outperform classical computers. And also the approaches to attacking these 2 questions will be quite different. And also, as a person who works in computer science, I need to be quite careful, because in computer science, there are very few things that we know with absolute 100% certainty, but we have very strong belief that there are some complexity theoretic assumptions that people believe they are true. So, for example, people believe that there are problems that we can efficiently verify on classical computers. We can check the solution, but we wouldn't be able to efficiently compute them. And we also believe that there are some problems that quantum computers would be better at than classical computers. Okay, so when we are talking about what problems quantum computers will be able to solve eventually, we can rely on many tools in the toolbox of a computer scientist. And these tools often help us to prove some rigorous speedup of asymptotic regimes. So we can tell you with very, very high certainty that we will have algorithms that will be much faster on quantum computers than on classical computers. For example, Grover's algorithm is such an example. However, when we are talking about asymptotic regime, it means that quantum computers will be faster than classical computers once the problems become very, very large. And in some cases, they might be absolutely huge. And that also means that to get to the regime, we will need to have very large mature quantum computers. So in many cases, they will need to have more than billion qubits, and we will need to also be able to correct and control these qubits very well. And this is what my research focuses on. I try to come up with applications of quantum computing in many different areas. And I try to err on the side of caution when I want to be quite certain that the things that I'm proposing can be proven. The other way of looking at applications of quantum computers is to think, what can we do with some number of qubits? And given that these numbers of qubits are generally quite small, we need to really carefully look for problems that would be extremely easy for quantum computers and would be much, much more difficult for classical computers. This is because with such a small numbers of computers, we can only look at problems that are very small or that have some difficult component that is very small. I mean, in truth, there are many, many difficult questions, but I hope to help you about the way of thinking about quantum algorithms that I try to employ when I read academic papers. So when I see a proposed quantum algorithm, I first look about the projected applications. Is this only a very pretty mathematical paper, or is this something that can be used in practice? The second question is, when can we expect to implement these algorithms? Do they require relatively small number of qubits, or will we need to wait 50 or maybe 100 years until we build a massive machine? And the last one is, how confident are we about the potential speed up? Is this just a conjecture? Are there authors saying, look, this is a really cool idea that we have, this would be worth trying? Or are they saying, we rigorously proved that this will be much faster than anything that people ever seen? So let me give you some examples. And I think there is no better place to start than the famous Shor's algorithm for factoring. So if you opened Nielsen and Chuang or any of the well-known quantum algorithms textbooks, you probably learned that quantum computers would be very good at breaking the existing cryptography. And Shor's algorithm, therefore, has a really big, massive application. However, when people carefully looked into where we can implement it, the last estimate that we have is that it would require 20 million of physical qubits. This is good news for cryptographer, but since we already only have qubit chips with about 50-ish qubits, getting to 20 million qubits will take some time. I should also know that this number will likely go down as we come up with better methods for autocorrections and better quantum computing primitives, but Shor's algorithm is quite intensive on the resources. And last question is, how are we confident about the potential speedup? And in this case, we are very confident. So this is a very rigorous algorithm and for a problem that has been studied for a long time. So we are pretty sure that for factoring, quantum algorithms will be faster than classical ones. A completely different problem is random circuit sampling, which you might not really know. But in essence, the goal of random circuit sampling problem is to take a lot of qubits, run a circuit that consists of some random gates, and then sample from the output. So measure all of the qubits at the end and report the outcome. This task is very easy for quantum computers. We essentially just run the circuit. And if it's big enough, we can tell that this will be a task that would be difficult for traditional computers. It's hard to say if we can still compute it with 50 or 60 qubits, but once the number of qubits gets large enough, let's say maybe above 100, we won't be really able to sample from this type of probabilistic distribution classically. What are the applications of this? Well, there aren't really any. This task was only conceived to demonstrate that quantum computers, even small quantum computers, can be much more powerful than classical computers. But if people really try, we could also use this application to create random numbers in a way that we would be able to certify that they are truly random. Random circuit sampling is one of the algorithms that can be implemented. In fact, it was implemented by the Google group in 2019. And at the time, they said that this task cannot be classically computed even in very large computers. But now we have classical computers that we have classical algorithms that improved a lot, but still quantum computers seem to be much faster than classical computers, even for fairly small number of qubits. And the last question about the confidence, we can say that if we believe some computer science conjectures, we can be very, very confident that indeed for random circuit sampling, problem that we don't really care about in practice, but there is a problem that quantum computers are really much stronger than classical ones. Let me give you one last example, quantum simulation. And this is the problem that is very often talked about, and indeed something that I myself work on. And in the problem of quantum simulations, we assume that we have some physical system. We know the Hamiltonian. We know how the system should behave. And our goal is to compute how this physical system would look in the future, how it would evolve in time. If we can do this, it would have many applications, for example, in quantum chemistry, material design, or even drug discovery. And the estimates that we have for a rigorous algorithm put this problem between 1 and 10 million qubits, based on there are some trade-offs between the number of qubits and the time we would need to simulate it. This is because most of the dynamic simulations are not known to be implementable in the NISQ regime. So we will need very deep circuits, and therefore we would need to have error corrections. When I think about the confidence about this not being an easy problem for classical computers, we need to look at two different cases. So if we only care about the simulation of the dynamics, we are very sure that this won't be easy for classical computers. However, if we start looking at applications where we have assumptions, or maybe we want to compute problems such as ground states or some properties of chemical molecules, we are much less sure what would happen. We know that in some cases, problems in quantum chemistry can be solved very well with existing techniques. We have lots of heuristics or other computational methods in computational chemistry that work extremely well. So in some cases, we don't really need quantum computers. And on the opposite side of the spectrum, we know that there exist problems that even quantum computers won't be able to solve. So the speedups for the textbook case is very, very clear. But once we still start looking at the applications, it becomes all over the place. And it becomes much more difficult to promise if quantum computers can actually help or not. Okay, so there are also some cases where quantum computers aren't really going to help us. One of the biggest problems is that the problem we want to solve is just too big, and we are not able to map it on the quantum chips. Also, if we need to load or store a lot of data, this would be very, very difficult, and it might kill all of the speed that we would achieve in data processing. Another case is where quantum computers don't perform a lot is when we need to perform a lot of arithmetics, or if the problems we are solving are very sequential, and superposition isn't going to help us a lot. So a takeaway for it is that even if we can map some problem on a quantum computer, it doesn't necessarily mean that it would be faster than solving the same problem on a classical computer. And in fact, looking at the speedups rigorously is something that can be quite complicated, and many people are studying it in academia and in industry from lots of different perspectives. So just to finish up, I would like to give you a few of my resources. And since I'm an academic and I'm more focused in computer science, these ones might be different than the typical textbook and resources that people are using. So I listed all of these textbooks or lecture notes, talks in the order of difficulty. I think the introduction to quantum computing from K. Laflamme and Mosca is a very good introductory textbook in the algorithms and in the mathematics that people typically use. And on the opposite side of the spectrum, if you want to learn about the cutting-edge research, there is this annual conference called QIP that always presents some of the newest results on the very theoretical side of quantum computing. And you can find the talks online, and also its papers will be published on arXiv. Thank you very, very much, and I would be more than happy to answer some questions.